We'll get started in a few minutes. I'll just wait for a few more people to join. Okay, let's get started. Good afternoon once again, and welcome to the live problem solving session for traffic engineering course. My name is Seri Vinayagam. I'm a PhD scholar in the civil engineering department at IIT Madras. Okay, so this is the second week of our sessions. Okay, so this week we'll be covering the lectures that were covered in the second week of the traffic engineering course. So as usual, we'll start with an overview of what was taught in this week, right? And then we'll continue with some questions related to those concepts, right? So that you will be facing in the assignments. So in this particular week, so again we had 5 lectures. So the first lecture was about traffic facilities and the traffic stream parameters. Right. So when it comes to traffic facilities, we have two broad categories that we looked at. One is the interrupted traffic facilities, and in the uninterrupted traffic flow facilities. Right. So what is the interrupted flow facilities? So in the interrupted flow facilities, so you will have external factors that affect the flow of the traffic, right? So we have the traffic stream. So the traffic stream has a speed, density, and so on, right? So those are the parameters. So these, if they are affected by anything other than the traffic itself, so then we call them as the interrupted flow facilities. So what could these be? So these could be, traffic signals, the stop sign, yield sign, right? So all these are factors that are external to the traffic stream and affects the flow of this, right? So the facilities that are having these kind of factors are called as the interrupted flow facilities. And then we have the uninterrupted flow facilities. So which is basically that doesn't have any of these external factors that affect them. Okay, can someone confirm if you are able to see the screen?
Yeah, sir, but now it is currently a blank screen.
Okay.
But I can see the screen before. Now only it is blank.
Okay, so let me just reshare. Yeah, is it visible now?
Yes, sir, yes, sir.
So and then we have the uninterrupted flow facilities, so which is basically that doesn't have any of these external factors that affect the flow of the traffic stream, right? So these are the two broad categories that we looked at, and then we had looked at different traffic stream parameters, right? So and these are broadly classified into two types, which are the macroscopic and the microscopic parameters. So what is macroscopic? So when we consider the traffic stream as a single entity, right? So we do not look at individual vehicles, but rather the traffic stream as a whole. And then when we the parameters that describe all this traffic stream as a whole is called a macroscopic parameter, right? The flow, speed, and density. So these are the usual parameters that we use to describe the traffic stream as a whole, right? So when we are not looking at individual vehicles, but the stream as a whole, so then we are looking at macroscopic parameters. And when we are looking at individual vehicles, right? So the measurements that we make with individual vehicles, like speed, can also be measured for individual vehicles, right? And then it will vary for each vehicle, right? So these kind of parameters, which depends upon the vehicle itself, right, and varies with the individual vehicle. So that is what we call as the microscopic parameters, right? So we looked at the headway, which comes in the later lecture. But these headways, these are dependent upon the vehicle or the vehicle pairs, right? So if you take different vehicle pairs, so you will get a different headway measurement, right? And that describes those that individual pair of vehicles and not the whole stream. So those kind of parameters are called the microscopic parameters. And in this particular lecture, we were looking at the speed characteristics, right? And looking at how that is different for the macroscopic and the microscopic scales. So when we are discussing that, we looked at two concepts, which are the time mean speed and the space mean speed, right? So why are we looking at this? So when we are talking about mean, so which means that there is the quantity that is varying, right? So that's why we are taking this average to represent a particular central value of this variable quantity, right? So we are looking at two kinds of means. One is the time mean and space mean. So we have to take this average or the mean over a particular axis, right? So when we are looking at time mean speed, that means the speed is, so time mean speed TMS, so which means the speed is varying over time. Time is the factor with which the speed is varying, right? So varying factor is time, and we are taking this average or the mean over the time axis, right? So which means you have a facility roadway, right? So time is varying, but the space is fixed. So you are standing at a point, and then you are measuring the speed of the vehicles which are crossing this particular point over a period of time. So you'll have multiple measurements at different points in time, right? T1, T2, and so on. And then you take the average of all the speeds, right, over the time axis. Then you will get the time mean speed, right? So time is varying, but the location is fixed. So when it comes to space mean speed, it is the other way around, right? So here we are not looking at a particular location, rather the whole stretch of the road, right? So where we have a stretch of the road and we have different vehicles that are present at a given point in time, right? So the time is fixed. So T is fixed, right? So for SMS, right? And then you take the average of the individual vehicle speed at the given point in time, that are present in the given stretch of the road, right? So that is your space mean speed. So the average is over the spatial dimension, right? So but the time is a constant there, right? So that's the space mean speed. And when we are looking at the traffic stream parameters, the speed that we are generally using is the space mean speed and not the time mean speed. Okay, so that's what we looked at in the first lecture. So in the second lecture, so we were looking at traffic volumes and traffic headways. So these are the other parameters other than stream. So when it comes to traffic volumes, we have different ways of measuring the traffic volumes, right? So we have the AADT, so which means annual average daily traffic. So which means we are looking at, annual means 365 days, right? So daily means the 24 hours, right? So we measure 24 hours traffic over all the days of the year, and then take the average of this daily hourly traffic, and that gives us the annual average daily traffic, right? So this are generally used. So when you are looking at bringing a new facility and you want to know what's the scale at which this facility is going to serve, right? So how feasible is it, whether you will have enough revenue or not, or what is the scale at which we are going to operate. So to get a sense of that, so you will be needing the AADT. So then we are having the annual average weekday traffic, right? So this is annual average, but only the weekdays. So which means it is still a daily count, right? So 24 hours we are looking at it, but we are not going to look at 365, but only the weekdays. So this is going to be for a lesser period of time, but still done, throughout the year, right? So then we will get an annual average weekday traffic, and then but these are generally not practically feasible, right? So you do not have you will not generally have that much time to count get the traffic volumes. So we go for some periods lesser than a year, so usually 1 or 2 weeks, and then we take the averages, right? So this is average daily traffic, right? So this is for 24 hours, but like 1 week or 2 week. So for a smaller period, then you get the average daily traffic. And similarly, when you do it for only the weekdays, you will get the average weekday traffic, right? So these are the different quantities that we measure for for the traffic volume, right? And then we looked at the Pcover factor. So what it is? So even though when we are looking at daily traffic, so but within a given day there is going to be hourly variation, right? So it's so the averages over a day is not going to be truly representative of what we are going to see on a hourly basis, right? So because there is a temporal variation, right? So at certain hours of the day there is going to be a very high traffic, and at certain time of the day there's going to be very low traffic or nearly zero traffic, right? So when we are designing the facilities, if we are going to look at the averages, it's possible that at certain periods the facility would fail in terms of that it may not be able to handle the flow that is coming. So that's why we have to look at the hours or the design for the hours where the the traffic volume will be higher. So that's where the peak hour factor comes into picture. So the peak hour factor is defined as the total hourly volume divided by the peak flow rate, right? So what is this? So when you look at a particular hour of the day, so what is the number of vehicles that are crossing that particular location? That's your total hourly volume. So that divided by the peak flow rate. So what is the peak flow rate? So there is what is flow rate? So flow rate is basically when you are measuring the volume in a particular period and express it in hourly volume, right? So you measure it for a period that is less than 1 hour, right? So usually 10 minutes or 15 minutes, but you express it as a hourly volume, right? So if you're measuring it for a period of 15 minutes, so you multiply it by 4 and express and say that is the volume per hour, right? So that's the flow rate. So what is the peak flow rate then? So within your peak hour, right? So you measure it for different periods of smaller lengths, right? So say 10 minutes or 15-minute periods, and then you see which period has the highest volume, and then you take that particular period's volume and multiply it by 4 if it is 15-minute period, and then you will get the peak flow rate, right? So this ratio of the total hourly volume to the peak flow rate will give you the peak hour factor, and this ranges from 0.25 to 1. Why? So because say when you have you're measuring the volume every 15 minutes, right? So when can this peak flow rate be higher? So when something has a maximum flow, right? Some particular period has a maximum flow, and so every other other periods have zero flow. So what is will be a peak flow rate? So peak flow rate will be Vm times 4. Right. So what is your total hourly volume? Your total hourly volume is Vm because it is a sum of all the 4, but the other 3 are 0. So then the ratio will be Vm by 4 times Vm, so which will be 0.25. Right. So this is the smallest possible peak hour flow, peak hour factor that you can get. So what is the other case? When will we get the peak hour factor maximum? So when there is equal volume that is occurring on all the 4 periods, so then your total hourly volume is also the same as your peak hour flow rate, right? So in that case your peak hour factor is 1, right? So this is the maximum. So the theoretical range of PHF will be 0.25 to 1. Okay, and then when we are looking at time headways, so when we talk about headways, there are two ways in which we can describe the headways, right? Similar to how we had the time mean speed and the space mean speed, headways can also be defined in terms of time as well as space, right? So when you consider two vehicles on the road, right? So for the time headway, what happens? It is the time elapsed between, right? So this first vehicle A, this is second vehicle B. So the front bumper of the first vehicle, crosses this point, let us say at time t. Then the front vehicle of this front bumper of this vehicle B crosses it at time B. Okay, TB is greater than TA. Right? B crosses at a later point in time. So the difference TB minus TA. So this is called as the time headway, right? So the difference in the time.
Sir,
T.
sir,
Yeah.
sir, sir, I have this doubt during the lecture itself.
Hmm.
Why is that the second vehicle is always higher than the first one, sir?
So this is because it is following, right? So So the second vehicle is going to cross this line at a later point.
Overtake.
Sorry?
It's going to overtake. So when it's come to overtaking, the B is becoming higher than the A. That concept is applied here as
No,
well.
no, it's
Overtaking
not. It's
concept.
not overtaking. Let us say the time is 4:4 at this point. Okay. So when it is going to cross this line, vehicle A is going to cross this line. Let us say at 4:5. Okay, that is TA. So vehicle B is behind vehicle A, right? So it is going to take more time to reach the same line, right? So let us say it is going to take 2 minutes to cross that particular line. So it is going to be say 647. So that is TB, right? So because vehicle B is behind vehicle A, it's going to take a longer time to cross the same point.
Okay.
So
So
that's why
that
TB
so
is
the
there.
B will be always higher than the A.
Yeah,
Okay.
yeah,
Thank you, sir.
yeah. So on this difference in this time taken, that is the time headway. So this is the time headway, and we also have the definition of space headway. So space headway is basically the distance between the corresponding points of the two vehicles, like the front bumper to the front bumper, whatever is this length that we have. So that is the space headway. So it need not be always the front bumper, but it should be the corresponding point. You could take the midpoint of this vehicle to the midpoint of this vehicle, or the back bumper to the back bumper, but it should be the corresponding points on the consecutive vehicles. So that will be your space headway. And then we also looked at the distribution. So why are we looking at distributions is because so this quantity, right? So the space headway or the time headway, we know this is a microscopic quantity, right? So which means that it is dependent on the pair of vehicles. So if we take any, some other pair of vehicles, right? So this value is going to change, right? And it's not easy to predict what this value is going to be because it depends on a variety of factors, right? Therefore, this is a random quantity, right? So it's not a constant. It's not going to follow a particular pattern. So we use the probability distributions to describe these random quantities, right? And we saw that there are different distributions that can be used to describe these random quantities, and the best fitting distribution is going to be dependent on the flow characteristics, right? So at low flow conditions, we saw that this negative exponential is it fits fairly well with the time headways. For medium flow conditions, we have the Pearson type 3, and for high flow conditions or the near capacity conditions, we have the normal distribution. So why is it? Because in low flow conditions, which means the flow is very low, so you could have vehicles that are closely following each other, or you could have vehicles that are very far apart, right? So anything is possible depending on the rate of flow, right? So that's why any all possible headways are equally likely to occur, right? So negative exponential is fairly a good fitting distribution for such conditions. And when you have very high flow rate, which means that every pair of vehicle that you consider is likely to have the same gap between them, right? So because the space in the roadway is limited, and when you have too many vehicles, so they are going to occupy the roadway very closely packed in a very closely packed fashion. So the gap between all of them is going to be roughly the same, right? So for those conditions, a normal distribution is a good enough approximation, right? Because a normal distribution looks something like this, right? So it's symmetrical, and its mean is somewhere here. So this is highly probable, and very high values or very low values are less likely to occur, right? So when you have medium flow, so it is basically between these two cases, right? It's not congested, it's not free flow also, right? It's not completely random, but it's not constant as well. So it's somewhere in the middle. So there a Pearson type 3 kind of distribution is a fairly good approximation. Okay, so then in the third lecture, so we looked at the traffic density and then the relationship among the macroscopic parameters. So when we talk about density, what is density? So density is basically the number of vehicles that are occupying the roadway at a given point in time, right? So you have the road, so you have a number of vehicles when you look at a particular time and a particular section. So there will be a number of vehicles that are there, and this we generally express it in per lane, right? So for each lane we generally calculate a density, right? So which means and also for a 1 kilometer stretch, right? So that's the standard that we use, the number of vehicles that are present in 1 kilometer in one day, right? So that's the density, and this density varies, right? So with the flow, right? So and then we have different or specific characteristics in terms of density. One is the jam density. What is jam density? Jam density is when the flow is nearly zero, right? So when the flow is zero, you have the jam density, and when the vehicles are closely packed, right? So the vehicles are occupying very the whole stretch of the roadway, and they are very closely packed. So you have in that case the vehicles will be stopped, right? So consider signalized intersection. So when there is a red signal, so the vehicles will be very closely packed and will not be moving. So that's the jam density condition. And then we have the optimum density. So what is optimum density? Optimum density is that density where the flow is high, right? So jam density will have zero flow. So optimum density corresponds to maximum flow, right? So I told that flow varies with density, but at one particular density, you'll be seeing the maximum flow occurring, and that particular density value is called the optimum density, right? And then we have another parameter, right? So called occupancy. So what is occupancy? So occupancy is basically, so when you would have heard about the loop detectors, right? So why do we use the loop detectors for? Loop detectors are used for counting in traffic counts, right? So how many vehicles are crossing that particular location, right? So for flow estimations, we use that loop detector, but it can also be used for finding occupancy. So occupancy is nothing but the percentage of time the detector is occupied, right? So if we are going to conduct this experiment, say for 1 hour, right, and then see how much time in that 1 hour a vehicle was present within the loop, right? So that is your occupancy. So why are we interested in looking at occupancy? Is because occupancy and density has a relationship, right? So it is expressed as the density K is occupancy divided by the average vehicle length plus the detector length. Okay, so we average vehicle length is V, and the detector length, so which is basically this part, right? So the occupancy by the vehicle length plus detector length, so that gives you an estimate of the density. And why is this important? Is because density is difficult to calculate from the field. Why? Because you need to look at the whole stretch of the roadway, right? Whereas for the loop detector, you just have to look at it at one particular point, right? So this is much easier to obtain. This occupancy value is easier to obtain than the density, right? So when you are looking at the practical aspect of it, so that's why we are looking at occupancy, because we can estimate the density given a particular occupancy value. Okay, and then we have looked at the fundamental relationship of the traffic flow. So what is the fundamental relationship of traffic flow? So we have the three basic variables. So that is the speed expressed as V, flow expressed as K, and density K, right? So these are the three fundamental parameters of traffic. So these are related as Q is equal to KV, right? So this is the fundamental relationship. So flow is density times the speed. Okay. So and if you look at the pairs of variables, right? So you will find the relationship to be like this. So the speed density relationship is like this. Sorry, the flow density, the speed density will be something like this, and the speed flow will be something like this. Okay. So when you look at this speed density relationship, so I said the jam density is when flow is zero, right? So this is that Kj, or the jam density, right? So flow can be zero when the density is also zero, right? So that is also possible, but the jam density is when the flow is zero, and but the vehicles are still present, right? So that's the jam density condition. And so this is the point where the flow is maximum, right? So the maximum flow is occurring, and corresponding to that, whatever is the density, that is called as the critical density. Okay, and then we also looked at, about the speed flow density or the fundamental relationships from a theoretical and practical aspect, right? So these are the theoretical relationships what we are having here. But when you measure these from the field, the speed values, flow values, and density values, and try to plot them, you will not always see, these nice looking curves. Why? Because there are, there's always noise in the data, and also there is issue of where you collect the data, right? It's not always going to be perfect. Like for example, when you have stretches like this, so this is called as a bottleneck. Why? Because the capacity is reduced at this location compared to its upstream or the downstream location, right? So which means the flow in this region is going to be affected much earlier than at the upstream or the downstream locations. So when you are measuring close to such bottleneck locations and somewhere away from this bottleneck locations, right? So when the theoretical relationships, so let us say this is A and B. So these are, let us say this is a 3-lane road. So because the capacity is same at both locations A and B, so theoretically you should see the same this fundamental relationship because the geometry characteristics are the same. But however, because this location B is immediately upstream to a bottleneck location, so some condition may also be observed at location B, which may not be present in location A, and therefore such issues may affect the when you are doing the studies with respect to this fundamental relations. So you should be careful about where you are measuring your variables from. Okay, so then in lecture 9, we looked at this single regime traffic stream models, right? So what are these traffic stream models? So this traffic stream models try to, quantify this fundamental relationship, right? So we have different models. So that's basically trying to relate these fundamental variables. So we have the single regime model, so which means that these models try to express the relationship using a single equation, right? So for example, we have the speed density relationship, right? So a linear line, straight line. So this means that at every value of density, for every portion, for every value of density, there is a single equation that tells you what the speed value is, right? A single equation is enough to represent this relationship between speed and density, right? So like that, so the single regime model uses single equation to describe the characteristics or to describe the relationship between these variables. So within that, there are a number of models. So the green shields model is one of the most popular models. So where the speed density relationship is expressed as, so V is equal to Vf minus uh, Vf by Kj into K, right? So V is called the free flow speed. So what is free flow speed? So when you have near zero flow, right? So that's the speed that you will realize at those flows is called the free flow speed, right? So that's the maximum speed that you will, find in a particular facility. So that's the free flow speed, right? So the flow happens freely without the interruption from any other surrounding traffic. And Kj, as we already saw, it is the jam density, and this is the relationship. So this is basically is giving you this linear relationship between the speed and density. So what happens here? So when K is 0, right? So when you put K is equal to 0, you will get V is equal to Vf, right? So that is the maximum value. And when this density becomes equal to the jam density Kj, so what happens? This Vf by yeah. So K becomes Kj. So and then Vf minus Vf, V will become 0, right? So that's this linear relationship between the speed and density given by the green shield model. So once you have this equation, you can always derive the other relationships. Why? Because the other parameters are related because Q is equal to Kv. So you know how Q and V are related. From this you can get how Q and K are related and how Q and V are related. Right? So as I said, this one equation is enough to represent the traffic in all the traffic conditions, whether it is free flow or in the congested state. Next, we have the Greenbug model. So what is the Greenbug model? So Greenbug model tells the V is equal to Vm log Kj by K. Right. So here this Vm is not your same as here V. So Vm is basically the speed that you will observe when the flow is at the optimum, when the flow is the maximum, right? So as I said, like, so we have the maximum flow occurs at some point. So when the free flow speed is there, you will not have the maximum flow, right? So free flow speed occurs when the flow is minimum. But this particular VM that is used in the Greenberg's model is the maximum flow, which is the speed corresponding to the maximum flow, right? But there is one problem with this particular model is when you have low flows corresponding to low densities, k is closer to 0. What happens is this quantity log of kj by k is going to be very large, and therefore we will be approaching infinity, right? So as k tends to 0, right? So this is not logical, right? So because speed cannot go to infinity, right? So there is a maximum limit, but this model does not account for that, right? So that's one of the negatives of the Greenberg model. So to address this, the Underberg model was developed. So the Underberg model gives us an exponential relationship. So what is that? So V is equal to Vf e to the power minus k by km, right? So here the free flow speed is used, but the instead of the jam density, the density corresponding to the maximum flow or the critical density is used in this particular model. But there is also a limitation with this model is when the density becomes jam density, right? So when k is equal to kj, so what happens? This particular ratio will be kj by km, which will be greater than 1 because the jam density will be higher than the critical density, right? So always. So at this point, so E is e power minus of that is going to be still some positive value, and that is multiplied by Vf is going to be again another positive value, which means speed is not equal to 0 when kj is equal to when k is equal to kj, right? So this is also not logical because at jam densities the speed is 0, right? So this part is not captured by the Underwood model, right? So that's the limitation. There are different limitations associated with each model, but the overall limitation is that a single regime cannot capture the complete state of traffic, right, in all conditions, right? So that's what we had when we were comparing these different models. And how do we calibrate these models? So we collect these parameters like speed, density, flow. So we try to measure these from the field and try to fit a curve based on the proposed equations. We try to fit a curve and then try to estimate the parameters of the fitted curve. So in lecture 10, we looked at the multi-regime models, right? So because we know the single regime model is not sufficient, so we went into multi-regime model. So where we divide the traffic states into different regions, right? Like free flow region, congested regions, and then try to come up with an equation that describes the traffic in each region, right? So which means we are going to have more than one equation, and that is applicable for different regions of the traffic states. So here we had the eddies model, like the two regime linear model, modified Greenberg's model. So these come up with different models at different portions of the traffic state, right? So we had multiple of these, and again the data collection for calibration for these models like similar. So again we'll collect the speed, flow, or density, and then try to estimate the parameters with respect to that equation that we are proposing. And finally, we looked at characteristics of interrupted flow. So as I said, interrupted flow facilities are those where there is some external factors. So we looked at two cases where we had a traffic signal and where we had a stop or a yield sign. Right. So how in a traffic signal, when you have traffic signal, so you basically have different characteristics associated with it. For example, when the traffic signal turns green, so you have vehicles that cross the stop line and go, and you measure the time it takes the vehicle for the vehicles to, or as the vehicles cross, you measure the time it takes to cross, and then you calculate the headway between the vehicles. So what you will see is basically a relationship like this. right? So initially, so this is the headway, this is the vehicle number, right? So for different vehicles, you calculate the headways, and what you will see is that initially it will be higher, but it will decrease and then become a constant value, and this constant value is called as the saturation headway. Saturation headway, and so the saturation headway basically tells you, so if the signal is going to stay green, right? So how many vehicles will be able to pass through that intersection in 1 hour, right? So the saturation flow rate is calculated using the using the saturated head, right? So 3600 by h, because h in seconds, so 3600 by h will give you the saturation flow rate. So that is basically like the capacity of that intersection. So it's a hypothetical case because the signal is not always going to stay green, but if it were to stay green for 1 hour, how many vehicles can pass through it, right? So that is one way. And then we also look at delays that are associated with the intersections to characterize those, or the performance of the intersection is defined in terms of the delays. So those are the concepts that were covered in week number 2. Now let's move into questions, okay, so related to these concepts. So the first question is, which of the following statements are true? So A is time mean speed is always greater than or equal to the space mean speed. B, time mean speed will be equal to space mean speed if the variability in the speed becomes 0 for any segment of the road. C, F test is used to test significant differences between means for any two samples of speeds taken from the same population. And D is the coefficient of variation normalizes the standard deviation. Okay, so I'll create a poll, and then when you are ready, you can choose one of the answer options from the poll. Okay, I have launched a poll. Let me know if you are able to see the poll.
Yes, sir.
Okay, so whenever you are ready, you can choose one of the options. Let me recreate, because this is a multiple answer question, so more than one option may be correct. Okay, so let me recreate the poll with different options. Okay, so we have a vote for A, B, right? So the right answer, so the right answer is options A, B, and D. Okay, so A, B are correct, but D is also correct. Okay, so why? Right, so we know that TMS is always greater than or equal to SMS. And when will it be equal? So it will be equal when all the vehicles are traveling at the same speed, right? So that is when there is no variation, right? So when all the vehicles are traveling at same speed, so that's the this variability part. So that's when TMS will be equal to SMS. If some vehicles are traveling at different speeds, so in that case, TMS will always be greater than the SMS. So that's why A and B are correct, right? So why? Because So when we are looking at the space mean speed, we are looking at all the vehicles in a particular stretch of the road, right? So which means all the slower moving vehicles will be considered. But when we are looking at time mean speed, we are looking at a particular point of this road. So which means that even though there are more slower moving vehicles, we'll not be considering all of these, in our time mean speed. So that's why slow SMS will always be lesser than, or in the worst case equal to, the time mean speed. So C states that F test is used to test significant differences between means. So that is false, because F test is used for checking if the variance is same between two population, right? So we don't use the mean F test for testing the mean. For testing the means, we have the Z test or the T test. Okay, and D is correct because coefficient of variation normalizes the standard deviation. So what is the definition of coefficient of variation? So coefficient of variation COV is nothing but sigma by mu, right? So what is sigma? Sigma is the standard deviation, right? So mu is the mean, right? So we are normalizing this standard deviation by the mean of the population, right? So if you have population, you take the values from the population. If you have sample, you take the corresponding sample values. So when we use sigma and mu for the population values, and S and x bar to represent the standard deviation and the mean calculated from the samples, right? So in either case, it is the standard deviation by the mean. So we are looking at normalized values of standard deviation with respect to the mean. So that means that, so if the mean is larger, your standard deviation is also for example, a particular value of standard deviation. If standard deviation is 10, right? So, but the mean is say 5 in one case, and the mean is 30 in one case, right? So, but sigma is still 10, right? So, if you just ignore the means, so then we'll say the variance in the data is the same in both cases, right? So, because sigma is 10. But in one case, the mean is 5, which means most of the values are smaller in this case. So, when most of the values are smaller, you have some values which are very large. That's why your sigma is 10. So which means there is a larger differences among the values in this particular case. Whereas when mu is 30, which means that most of the values are higher, right? So because the mean is large. So in that case, when you have a difference, a standard deviation of 10, which means that there is not as a high variation as we saw in the first case, right? So that's why COV, when you do 10 by 5 and 10 by 30, so you will have a better picture rather than looking at just the standard deviation alone. So that's why we go with COVs. And so, but the statement says that it normalizes standard deviation. So that is correct, because that's by definition how COV is defined, right? So D is also correct. Okay, so the second question is to calculate the maximum flow on the road if the flow density relationship is given as given here. Okay, so Q is 215 times V minus 41V log V, where V is in kilometers per hour and Q is in vehicles per hour. So you can use the chat for this. Once you solve it, you can put it in the chat. Okay, any answer? Do you need more time?
Yes, sir.
Okay.
Sir, I don't know what to apply for a case. In the lecture itself, I have some slight doubts in this step, sir. Please help me with this by solving them, sir. I'm trying only, but I can't
Okay.
find the.
Okay, so okay, I'll explain in that case how do you solve this one. Okay. So the answer is 2857, but let's see how will we arrive at this. Okay, so we have been given this relationship, right? So Q is equal to 215V minus 41V log V, right? So that's the one. 215V minus 41V log V. So this is the function, right? So this is the function, a flow as a function of speed, right? So how do you find the maximum or the minimum of function? So you basically differentiate that function with respect to the variable that is used in the function, and then you set it to 0, right? So you find where the inflection point is, right? So at the inflection point, you either have a maximum or the minimum, right? So that's the first principle, right? So df of x by dx equal to 0, right? So wherever this happens, right? So wherever the derivative becomes 0, that's where either you reach the maximum or the minimum of the function. Okay. So, and to double check whether it's the maximum or the minimum, you find the second derivative, right? So d squared f of x by dx square. So if this is greater than 0, it means that it is a minimum point, and if it is less than 0, that particular point is the maximum point. Okay, so that's how you will find the maximum or the minimum of a function. So here, so the f of x is nothing but q of v, right? So q as a function of v is what is given to us. So what we need to do is you need to find the differential of this function with respect to v, right? So we have to differentiate this particular equation with respect to v and set it equal to 0. So that will give us the inflection point. So how do we do that? So dq by dv, what is that? So 215v. So the derivative of that with respect to v is just 215, right? And then we have minus 41 times v log v. Okay, how do we differentiate v log v? We have to apply the chain rule. So it is v into differential of log v plus differential of v into log v. So differential of v is what? It is just 1. So it is log v plus, what is the differential of log v? It is 1 by v. So v into 1 by v, right? So we have just differentiated this. So if we simplify it, so it will become 215 minus 41 into, so v into 1 by v will become 1. So it is just 1 plus log v. Okay. So this is what? This is the differential of dq with respect to v, right? So how do we find maximum? So we have to set this equal to 0. So dq by dv equal to 0. So that means 215 minus 41 into 1 plus log v is equal to 0. So which means 215 by 41 minus 1 is equal to log v, right? So from this we have to find what v is, right? So v comes out to be 69.68 kilometers per hour. Okay, so or whatever is the unit, we don't have the units here, assume it to be kilometers per hour. Okay, so this is how so when v is 69.68, so the differential of q with respect to v is 0, right? So this is the point of inflection. So q could be either maximum or minimum at this point, right? So when v is 69.68, but you can double check this, you can differentiate this again with respect to v, and then see that it will be less than 0, which means this point is where the q will be maximum. Okay, so is it clear up to this point what we have done?
Yes, sir.
Yeah. So now our question asks us to find the maximum value of q, which means we have to plug this value v back into our equation, right? So q of v, which is 69.68. So at 69.68, what is the value of q? So that is the maximum flow. So which is 215 times 69.68 minus 41 into 69.68 times the log of 69.68. So this comes out to be 2857. Okay, so that's how we find the maximum flow. Right. So for the other models, the different the Greenbug model and so on. So this is how we find it there as well. So we had the like the QK the VK relationship, right? So V is equal to Vf minus Vf by Kj into K, right? So we find Q is equal to Kv. So we plug this V back into this equation to get the QK relationship, right? And then we differentiate Q with respect to K to find out where the maximum flow occurs, right? So to find the critical density. And if you use the VK relationship, or if you plug K here and then differentiate with respect to U, you'll find the maximum speed corresponding to the maximum flow, right? So that's how we find it in the other models as well. But here, this is not from any standard model, right? This is a different equation, so we have to differentiate here. We cannot use the predefined formulas. Okay, so but this is the general procedure you follow to find the maximum or minimum of any function. Okay, so question number 3 is, which of the following statements is false with respect to the time headway distributions? So A is negative exponential distribution closely matches with measured time headway distribution when there is little interaction between vehicles in the traffic stream. B is Pearson type 3 distribution closely matches with measured time headway distribution at all levels of traffic flow. And C is normal distribution closely matches with measured travel time at near flow capacity conditions.
Sir, I think B is false because it intermediate time distance only it's measuring now, sir. Yes, sir.
So there is one more option. Yeah, so the right answer is actually option D, none of these. So why? Because Pearson type 3 is when you consider all the three distributions that we have discussed, the negative exponential, normal, and Pearson type 3. So negative exponential is good for the low flow conditions. Normal distribution is good enough for the near capacity conditions, right? So but these distributions, when you look at for the other flow condition, like negative exponential for the intermediate flow or the high flow, it's not very close to what we see in the field. So the normal distribution also for the low flow and the intermediate flow conditions, it won't be matching closely, right? So they do well at their given levels, but for the other levels they don't do that well. But when you take the Pearson type 3, it matches closely for the intermediate stage, but for the other two flow levels also, it gives a much closer, it's not way off for the other flow levels as well. So it gives a reasonable performance for all the three, traffic flow conditions. So that's why Pearson type 3 is good for all traffic levels rather than going with the negative exponential or normal distribution. Is that clear?
Yes, sir.
So the right option is none of these. All the three statements A, B, and C are correct. Okay, question number 4 is again, which of the following statement is false with respect to traffic density in qualitative terms? So A is at high densities, user experience a poor level of service and the productivity in terms of vehicle kilometer goes down. At low density, user experiences good level of service and the system is serving all the demand. C, system reaches optimum productivity in terms of vehicle kilometers travel at medium density with users experiencing highest level of service, and D is none of these.
Sir, I think all the statements are true, sir.
Okay. So the right answer is actually option C is not correct.
Okay, okay, sir.
Okay, so option A is high traffic density. So at high traffic density, what we have a congested state, right? Which means that the level of service is poor because the flow goes to zero, the speed also drops to zero, right? So which is a poor level of service. So the system productivity in terms of vehicle kilometers of travel, because the speed goes down, the flow goes down, so the vehicle kilometer travel also goes down. So which means the productivity is affected. So A is correct. So B says at low traffic densities, user experience a good level of service and the system is serving all the demand, right? So which means the flow is less than the capacity, right? So which means the system is able to serve all the demand, right? So whatever is coming in is able to go out at a good speed as well, because the traffic density is low. We know at low density speeds are high. So therefore the overall level of service is good. So B is also correct. So C states system reaches the optimum productivity in terms of vehicle kilometers at medium traffic density with users experiencing the highest level of service. So, but this is, we are looking at qualitative terms. So, which means medium traffic density is not, how do you define what a medium traffic density is, right? So with respect to some models, Greenbug models, so you will have, like at the midpoint is where the critical density is. So you have 0 and kj and critical density, but it's not always true that your critical density has to be in the midway point, right? So critical density could be at any different level as well. So you have some other, like triangular models, you will have something like this. So it's not always at the midpoint, right? So that's why you cannot always say that it is the medium traffic density. It's not closer to kj, but it's not always in the midpoint as well. So that's why you cannot always say that it's a medium traffic density where the q will be equal to q max, right? So that's why it is not always true. So C is incorrect. Okay, question 5, another numerical. So if the observed time headway in a one-way homogeneous traffic stream is 12 seconds, then which of the following describes the, sorry, yeah, which of the following describes the relationship between the space mean speed and the distance headway? So options are given. So V is 0.6 h, V is 0.3 h, V is 0.2 h, and V is 0.5 h. Okay, any answer? We have to make use of the fundamental relationship of traffic stream in order to answer this one. Anyone? Any answers? You can answer on the poll. Shall I wait for some more time or shall we look at the answers?
We can look at the answers now.
Okay. So the right answer is option B. Okay, but we'll see how to arrive at that. Okay, so B is the right one, but how do we get there? So what do we want? We want to relate the space mean speed with the distance headway, right? So which means the space headway, right? So space headway is some h and the space mean speed is v. So we want to know what is the relationship between v and h, right? So what do we know? The relationship that we know between the fundamental parameters is that q is equal to kv, right? So flow is the product of density and the speed. So in the overview, I mentioned this, that the v that we use, the speed that we use in this fundamental relationship is the space mean speed and not the time mean speed, right? So the v here is the v sms. Okay, so we want the relationship between v and h. Okay. Yeah. So which means that there are two other, so V is what we want, so we don't have to do anything with V, but there are two other parameters Q and V which we need to substitute here. So how can we get first the density, right? So how is density and the distance headway related? So density, uh, so we know the definition of density is how many vehicles there are in a particular stretch of the road, right? So in 1 kilometer of the road, how many vehicles are there? So what we are given is the distance headway. So what is distance headway? It is basically the distance between the corresponding points of successive vehicles, right? So this distance, like from the front bumper to the front bumper, the distance is h, and this value we know. So it is, we can assume that this is constant, right? So let us assume this is the average headway. If we take any pair of vehicles, this is the expected value that we are going to have. So which means when we take 1 kilometer stretch of this roadway, right? So then how many vehicles will we find if the distance between two vehicles is h? So that will be nothing but, so if you convert this into meters, so this is 1000 meters. So 1000 by h, right? Because between every pair there is h distance. So in 1000 meters, 1000 by h number of vehicle pairs will be present, right? So this is the density, right? So this is density. So we can substitute that. So Q is equal to 1000 by h into v. Okay, so we have the v and h in the equation now, right? So but there is one more unknown, which is q. So how do we get q? That's where we need to make use of the other piece of information, which is the um, time headway that we have. So how is the time headway related to the flow? So what is flow? Flow is basically how many vehicles are crossing a particular location L. Okay, so how many vehicles are crossing this location L in 1 hour, right? So here we know the time headway is 12 seconds, which means every 12 seconds, so there is one vehicle, another vehicle. So every 12 seconds, there is one vehicle crossing this particular location, right? So that's how we will get the time headway as 12 seconds, right? So which means the time gap between any successive vehicle is 12 seconds, which means every 12 seconds one vehicle is going to cross a given point on the road, right? So then the flow, so if in 1 hour, how many 12 seconds do we have? So 3600 by 12, right? So this is the number of 12 seconds that we have in 1 hour. So and every 12 seconds we have one vehicle crossing. So then the flow will be 3600 by 12. So which is nothing but 300 vehicles per hour. So we know that unknown as well. So we substitute Q as 300. So 300 is equal to 1000 by h into V. So therefore V is equal to 300 by 1000 to h, which is equal to 0.3 h. Okay, so that's how we got the right answer as. Okay, is it clear? We arrived at this relationship. Any doubts?
No, sir.
Okay. So all you need to remember is this fundamental relationship. This is very important. Q is kV, and also the fact that the V that we use in the fundamental relationship is the space mean speed and not time mean speed, and how headway is related to density, right? So density is the length of the road divided by the space headway, and flow is related to the time mean speed, right? So flow is the time period divided by the time mean speed, right? So using those relationships, we can arrive at this SMS to the distance headway relationship. Okay, sixth question is, so we are given a statement, we have to say whether the statement is correct or not. So if it is correct, we will accept it. If it is false, we will reject it. Okay, the statement is congestion is observed only at interrupted flow facilities and not at uninterrupted facilities.
Accept.
Okay, so everyone can participate. So if you can answer in the poll, it will be better. So choose either A or B. Okay, so we have two answers so far. Any other answers? Okay, so the right answer is reject because the statement is false. Why? Because it says congestion is observed only at interrupted flow facilities and not at uninterrupted facilities. Right. So this is false. Why? Because when we defined the facility types, so we said in interrupted flow facilities, there will be external factors external to the traffic stream. Right. So external factors to that traffic stream will be present and that affects the movement of the vehicles in it, whereas uninterrupted facilities does not have those external factors. So that is the difference between these two. That does not mean there is no congestion in the uninterrupted facility, right? So for example, there is no signal. If there is no signal, does that mean that road will never be experiencing any delay? Right. So if more vehicles are approaching that way, that facility than its capacity, then delay will still be occurring in that, even if there is no signal or stop sign or anything, right? So, for example, if one facility, a roadway can cater to say 2,000 vehicles in 1 hour, right? But suddenly 3,000 vehicles are going to enter that facility. So, what will happen? The speed is going to drop down. It's going to get congested, right? So, when the demand, exceeds the capacity, you will always face congestion, right? So this is not dependent on whether or not you have an interruption or not, right? So if there is external factor, congestion will be present when that factor is working. But even if it is not there, depending on your flow to capacity ratio, you will have congestion in the uninterrupted facility as well, right? Just the what causes that congestion will be different, but it can still be present in both facilities, right? So that's why this given statement is not correct. Okay, so next question is, at forced flow conditions, the rate of flow is computed using the fundamental relationship of traffic flow, Q is equal to KV, which represents the average of all points within the defined section. Any other answers? There is one answer for A. Okay, there is one for B. Okay. So the right answer is A, that we accept the statement, which is correct. So basically, when you look at the traffic regimes, so we'll have broadly, two regimes, which is the free flow condition and the congested conditions, right? So this free forced flow condition is nothing but the congested regime. right? So when you have the QK, so this is your free flow side and this is the congested side, right? So we are looking at the congested regime. So in this, the rate of flow is computed using the fundamental relationship. It represents the average of all points in the defined section, right? So you take a particular stretch of the road, right? So and then you are measuring, say, the density at different for different sections, or the flow at different sections, right? So the flow is not going to be the same everywhere in the congested condition, right? So for example, when the congestion clears, the flow will be higher here, but these vehicles will still be stopped, right? So it takes some time for so you'll see that in the next week where we'll be looking at shock waves for the traffic state that is occurring here. To reach this point in a congested state, there will be some delay happening, right? So when the congestion clears and vehicles start moving, it's not like all the vehicles in the entire upstream sections also start moving immediately. So this may be starting to move at, say, t is equal to 0, then the vehicles here will take some time to move, right? So for example, say after 5 seconds, right? So which means when you are measuring the flow, so there will be non-zero flow here, but there will be zero flow here because everything is initially congested. So that's why. So the relationship that we are looking at is going to be the average relationship in the whole section, not at any particular. It's not going to be the same at all the points. But whereas when you are in a free flow conditions, right? So the vehicles is not going to be closely packed as in this case, right? So there is not going to be much interaction between the vehicles. Like each vehicle is moving on its own without any external stimulus, right? So it's not its speed or it's not affected by its surrounding vehicles. So which means you're going to have roughly the same value of flows at any point that you're going to measure, right? So that is in the free flow condition. So that's why this statement is correct. So in the forced flow condition, so it is the average of all the points, whereas in the free flow conditions, it will be the same everywhere. Okay. Next question is, coefficient of variation is a better measure of speed variations compared to standard deviation. Yeah, one answer A. Any other answer? Okay, so you have two answers for option A. So the right answer is also option A. I think we already discussed in earlier. So when we were looking at the concept of COV, so we have the standard deviation sigma and the coefficient of variation defined as sigma, the ratio of sigma to mu, right? So as we already saw, for example, when you're looking at two populations, A and B, for example, say two locations, right, A and B. So in A, we have speeds where the average speed is, say, 20 kilometers per hour, and in location B, the average speed is 100 kilometers per hour, right? So which means there are more faster moving vehicles in location B, whereas there are more slower moving vehicles in location A. But let us say the standard deviation is the same, okay? Say 10 kilometers per hour in both cases. So in this case, if we just look at standard deviation, we are going to say the variability in the speeds is the same in both locations, right? So but actually that is not the case. Why? Because so in location B we have very fast moving vehicles. So in that case, so we have 100, so we have 90 to 110 on average is the variation, right? So in the speeds, whereas in location A we have say 0 to 30, right? So even though the range is the same, but this is a larger variation in the speeds compared to the average that we are seeing, 20 kilometers per hour. 0 to 30 is a much higher variation compared to 100. So when the speeds are 100, so 90 to 110 is not a big difference in the speeds that we are looking at. So that's why when you calculate the COV, this will help us understand this difference much better. So when you calculate it, it will be 10 over 20, so which is 0.5, whereas here it is 10 over 100, right? So which is zero point 0.1, right? So which means location A has much higher variability than location E, right? So that is obvious when we are looking at the COV, which is hidden when we are just looking at the standard deviation itself. Yeah, that's why we are accepting that given statement. The next question is, both space and time headways are microscopic traffic stream parameters. Okay, one reject. Any other answer? Okay, so we have one accept and one reject. Right answer is actually we accepted. Why? Because so what is the difference between macroscopic and microscopic parameters? So macroscopic means that parameter defines the entire stream, right? So that particular value, like the space mean speed, time mean speed, the flow, the density. So these parameters is not specific to one vehicle or a pair of vehicles. It defines the whole traffic stream, right? So microscopic is, it depends, those values depend on the vehicle that you are choosing, or the vehicle pair that you are choosing, looking at, right? So for example, individual vehicles speed, not the time mean speed or space mean speed. Individual vehicle speed, its acceleration value, deceleration value, right? And the time mean speed and space mean speed, so how is that defined? It is defined for every pair of vehicle, right? So you take two vehicles A and B, and then you calculate the time elapsed to cross the given location for A and B. So that is your time headway, or the physical distance between the corresponding point, that is your space headway. This value is not the same for the entire traffic stream. You take some other vehicle C and D, right? So this gap is going to be different, right? So therefore, this both time headway as well as space headway are dependent on the vehicle pairs, right? So it's not a value that is defined for the entire traffic stream that you will see in the entire stretch of the roadway, right? So because this is going to be varying and dependent on individual vehicles or vehicle pairs, this is a microscopic parameter, right? That is by definition of how we are characterizing them. Okay, so that's why the given statement is correct. Okay. Next question is the fundamental relationship of traffic flow Q is equal to KV. The speed V is the space mean speed of the traffic stream. This should be easy because I already gave the answer in one of the earlier question. Okay, one accept. Yeah, so two accept. So that is correct because as we already saw in that question, the V in the Q is equal to KV is VSMS and not the VTMS, right? So when we are talking about this fundamental relationship, we always talk in terms of the space mean speed. Okay. Good. Question 11 is the theoretical speed flow curve is the same for two locations that have the same traffic demand but different capacities, which means Q is same but that KCR is different. So in that case, will the speed flow curve be the same? Okay, one reject. Any other answers? Okay, two rejects. So the right answer is also reject. Why? Because so as we know, the maximum flow occurs at the critical capacity, right? So if the capacity is different, which means the maximum flow will be different, right? So for one location you have KCR1 and for the other one KCR2, right? Clearly the relationship between Q and K is it's not going to be the same, right? So that's why they cannot have the same theoretical speed flow curve. Okay, so question 12 is Eddy's model is usually unable to predict speeds at low densities. One answer as B. Okay, one accept, one reject. All right. So the right answer is that we reject this. Why? Because what is Eddy's model? Eddy's model is a it's a two regime model, right? So it is one of the multi-regime models that we saw. So where it's basically a combination of the Underwood model and the Greenbug model, right? So what is so these two are the single regime models that we saw. So what was the problem with Greenbug model? So Greenbug model basically gives you, a constant, speed flow, sorry, a linearly decreasing speed flow relationship, right? So but usually that is not the case, because in free flow regime we will not, so when you draw the qk relationship. So when you connect any point from the origin, so that will be the speed. The slope of that line will give you the speed of the traffic state. So what you will be finding is, as your density increases, your speed is gradually decreasing even in the free flow regime, right? So, but that is not true. But what we see in reality is that speed will be fairly constant up to certain level, right? And then only it will start decreasing. It won't initially start decreasing from the free flow. So for some densities, free flow speed will be maintained. So that is not captured by the Greenberg model. So in the free flow regime, it fails to represent the reality. Whereas the Underwood model, what we saw, it's that its relationship, in the congested state, it won't reach zero, right? So it will reach to some smaller value, but it will never reach zero even at the jam density. So that was the issue with the Underwood model. So what Eddy's model did is, it took the Underwood model for the free flow regime, and it took the Greenberg model for the congested regime, right? So that combination gives us the Eddy's model. So when it takes the Underwood model for the free flow regime, so which means that the Greenberg's limitation is overcome. So Greenberg's model was having this limitation that it was not able to predict the speeds correctly at low densities, but that is overcome in the Eddy's model by considering the Underwood model, right? So uh, therefore this given statement is incorrect, right? It is good in the predicting speeds at the low densities as well. Okay, next question is, Q discharge rate is always greater than the capacity of the undersaturated portion. Okay, so we have reject. So the right answer is also we reject it. So why? Because so we are talking about Q discharge rate and capacity at undersaturated conditions. So when does a Q form? Q forms when you have saturation condition, right? So when you have higher demand than the capacity, right? So than what the facility can serve, that's when the Q of the vehicle start building up, right? So we are comparing the flow that is happening when in the congested state, from the congested state, and also flow that is happening in the non-congested state, right? So the capacity, when you're calculating using undersaturated condition, which means the vehicles will be able to travel faster right, or at a higher rate when you are having undersaturated condition, right? So the capacity that you calculated using that will be actually larger. So when you have the congested state, you will not always have realize the same capacity, right? So as you calculated in the unsaturated condition, they will not be traveling at the same rate, right? So therefore this will all be actually at a smaller rate. The Q discharge rate will be smaller, not greater than the capacity of the undersaturated portion, right? So that's why the statement is false. Okay, next question is about the peak hour factor, right? So if we have a 15-minute analysis period and then calculate the peak hour factor, then which of these given statement is incorrect? So option A is theoretically PHF cannot be greater than 1. So option B, when there is no flow variation within the hour, then the maximum PHF is achieved. And C is if all the hourly volume occurs in a single 15-minute interval, that's when we reach the minimum PHF. And D is the theoretical minimum value of PHF can be 0. So one of these statement is false. So which is that one? Okay, so we have one answer for option B. Yeah, so we have two answers, both option D. So both are correct. Option D is the right answer, right? So how is this? So PHF is what? PHF is, so when you are considering this 15-minute analysis period, so say the volumes in the first period is V1, V2, V3, and V4, and let us say V3 is the maximum of uh, all the four. So then PHF will be V1 plus V2 plus V3 plus V4. This is the hourly volume, right? So the actual hourly volume divided by the peak flow rate. So peak flow rate is nothing but, so considering the maximum flow in the period and assuming that that is going to be there in all the four periods, so then that is what we will get as the maximum flow rate, right? Or the peak flow rate. So then the PHF will be the sum of all the volumes divided by 4 times the maximum flow rate, which in this example it is V3. Okay. So option A says that theoretically PHF cannot be greater than 1. So which is correct. Why? Because see, V3 is the maximum out of V1 to V4, right? So 4 times of V3 is going to be greater than or equal to the sum of v1 plus v2 plus v3 plus v4, because each of these, so when you are doing v1 4 times v3, we are adding v3 4 times, and we know v3 is greater than v4, v2 and v1. So this sum is always going to be larger, which means denominator is going to be larger than the numerator. That's why this ratio cannot be greater than 1. So option B, when there is no variation in flow within the hour, theoretically minimum PHF is achieved. So which means what? So V1 equal to V2 equal to V3 equal to V4. So that is when the numerator and the denominator will become or yeah, so that's when the numerator sum is the minimum, right? So this ratio will be the minimum. So let us say all of them are equal to V3. So it will be 4 times V3 divided by 4 times V3. So V3, Yeah, so that time it will become 1. So that's when the maximum value is achieved, right? So the maximum value is basically 1, right? So when there is no variation, which means all the periods have equal flow. So that's when the ratio becomes 1, which is the maximum value. So option C is about the minimum value. So minimum value occurs when the entire hourly volume occurs in a single 15-minute interval, which means that we said V3 is the maximum, and that is equal to the peak, the hourly flow, which means in other periods no flow occurred, right? So which means V1, V2, and V4 are 0. So the numerator is just V3 because other three are 0. Denominator is 4 times V3, right? So this is when the ratio is at its minimum, so which is basically 1 by 4.25, right? So this is the minimum value, and this is the scenario in which it occurs. And D is the theoretically minimum value of PHF can be 0. So this is incorrect. So because we already saw the minimum value is 0.25, right? So it cannot be less than this, right? So if your flow is occurring, so the minimum that it can achieve is 0.25, and it cannot be less than that theoretically, right? So that's why option D is the incorrect one. Okay, question 15 is again about the traffic regime model. So we have to choose which is incorrect out of these. So option A is Greenbug's model can be used in the congested flow regime. B is Underwood's model does not represent zero speed at high concentrations. C, Eddy's model uses Underwood's in free flow regime and Greenbug's in congested flow regime. And D, in modified Greenbug's model, Underwood's model is used in a free flow regime and Greenbug's model is used in a congested flow regime. Any answers? Okay, we have one answer for B. Okay, another answer for C. All right. So the right answer is actually option D, right? It's not. So here we are talking about false statement, right? We have to choose the one that is not correct. So option A is Greenberg's model can be used in congested flow regime. So this is true because we already saw the limitation of the Greenberg model is in the free flow regime, right? So where the speed, starts decreasing with increasing, density, even at low density conditions. That is not true. So, but in the congested flow regime, it is fine, right? So there we can use the Greenbug's model. So A is correct. B is Underwood's model does not represent zero speed at high concentration. So this is also correct, right? So Underwood model has a problem at the high densities. Why? Because what is Underwood's model? It is Vf e power minus k by k, right? So that's the speed density relationship by the Underwood model. So here, so high concentration, when you look at kj, substitute that, so it becomes Vf e power minus kj by km, right? And we know that kj by km is greater than 1, and e power minus of that is still some positive value, right? So which means this product, Vf into that is non-zero, is some value greater than 0. So that is not correct, right? It does not go to 0 even when k is equal to kg, right? So that is also correct. So option C, Eddy's model uses Underwood's model in free flow and Greenbug's model in congested flow. This is also correct, right? So as I said, Eddy's model is a multi-regime model that tries to overcome the limitations of these two, right? So Greenbug has a limitation in the free flow part, Underwood model has a limitation in the congested part. Eddy's model is just using them in the using the best of these two models, right? So it is using the Underwood model in the free flow and Greenbug model in the congested flow regime, right? So that's why that is the Eddy's model. So C is also correct. So D is the incorrect one. So where in the modified Greenbug model, Underwood model is used in free flow and Greenbug is used in congested flow. That is incorrect because this part is correct. Greenbug is used in the congested flow, but it's not using Underwood model in the free flow regime, but a constant speed model, right? So in the modified Greenbug model, we have a constant speed for the free flow regime, and then the a decreasing speed as given by the Greenbug model in the congested regime. That is the modified Greenbug model. Okay, so but the given statement is wrong. That's why D is the right answer. Okay, so next is a numerical. So we are given hourly volumes in highways eastbound and westbound direction as 1700 vehicles per hour and 2600 vehicles per hour during the peak hour. Estimate the directional split factor B in the peak direction. Right, so this is for the same road but in two directions, right? So east direction and west direction. So we have two different flows measured during the peak hour. We have to find the directional split factor. So it can maybe take a couple of minutes. Any answers? Any answers? Do you need a minute more, or shall we look at the answer?
We can see the answers.
Okay. So the right answer is the directional split is 0.6. The directional split factor is 0.6047. Okay, but how do we calculate that? Right. So where do we use this directional split factor? So we know when we are we looked at different ways of measuring the traffic volume, right? So AADT, AAWT, ADT, and so on, right? So but when you are designing a facility, right? So we design it for the the peak conditions, right? So because that's the critical one that we need to be able to handle, right? So we do not basically design for the annual daily averages, but for the peak hour traffic flows. So which means that we need to know the design or the directional design hourly volume, right? So DDHV, right? So and this, yeah, and this is directional, right? So which means for either directions, so we need to find out what is the hourly design volume, right? So which is basically the maximum that we are going to handle, right? So for estimating that, so that's where we use the D factor. So how is that defined? So DDHV is basically AADT times D times K, right? So this is the annual average daily traffic, right? So we take the annual average, and this annual average daily traffic is does not differentiate between the different directions, right? So when you have two directions, so this annual average daily traffic contains both, right? So we take the flow in both directions and then take the average of that. So which means it contains both direction flows. So that's why when we are looking at a particular direction D, we are multiplying it by the proportion of traffic that goes in that direction. So if the total volume is V, and say 60% flows in one direction, 40% in the other, so then D for the direction that we are looking at, so will be either 60 or 40% depending on the direction that we are using, right? So that's the D factor. And K is basically, so even after we multiply with D, this is still the daily average for that particular direction, but we want for a particular hour. So, right, so and that hour is the peak hour, and K is basically the proportion of the daily traffic that happens in the peak hour, right? So we take the directional proportion and the hourly proportion and multiply AADT with that to come up with the directional design hourly volume. So that's where we need the directional factor. And how do we get that? Is, so we are given the flows in both directions, 1700 and 2600, and we want to estimate the D factor for the peak direction, right? So we can calculate for both directions, but in this question we are only concerned with the peak direction. And how do we determine which is the peak direction? So in the peak hour, whichever direction is going to have the highest flow, that is the peak direction, right? So in the peak hour, the westbound direction has the highest flow, 2600. So which means the westbound direction is the peak direction, and for that peak direction we want to find D. So how would we find? So what is this proportion is basically out of the total flow in that hour. So in both directions, how much is what percentage is going in the west direction. So how do we find what is the total flow in the peak hour? It is 1700 plus 2600, right? So this is the peak flow, or let us say total peak flow. Okay, so we are not differentiating the directions. In both directions together, this is the total flow that is happening.
Sir,
Yeah.
eastbound only having highest number of flows, sir. 1700 vehicle per hour. Then. Oh, sorry,
Okay.
sir. I thought it is 260. Sorry, sir.
Okay. Okay. It's 2600. So the total peak hour flow is 4300 vehicles per hour, right? So that is the total. So out of this 4300, what percentage is traveling in the peak direction, right? So that's what we are trying to find. So how do we find that? So D for the peak direction is 2600 out of 4300, right? So 2600 vehicles out of the total 4300 is traveling in the peak direction. So that is the proportion. So which comes out around 0.6. right? So basically the ratio of the peak direction flow to the total flow in the peak period will give you the directional split for the peak direction. Okay, so it's actually 0.6047. Okay, so any doubts in that? Is that clear? How do we estimate D?
Yes, sir.
Okay. Okay, so the next question is the projected AADT of a proposed facility is 31,000 vehicles per day. If the proportion of AADT in the design hour is 12% and the peak hour directional distribution is 63 is to 37, so in percentage, estimate the directional design hourly volume DDHV. Just exactly based on what we did in the previous question. So we have everything. We have AADT, we have the D, we have the K as well, right? So the peak our directional distribution is basically the K factor. So you want to use these and find the DDHV. Any answer? I think this is straightforward, right? So sorry, this is the K factor, this is the D factor, but it doesn't matter. 12% is a K. This is the directional split. Okay, 7.6. Okay. Any other answers? All right. So the right answer is actually 2344 vehicles per hour. Okay, so that's our directional design hourly work. So as I said, so AADT is DDHV is related to AADT like this. AADT into the directional split factor into the peak hour factor, right? So the peak hour proportion. Okay. So AADT is 31,000 right? So vehicles per day into what is the directional split. So it is given as 63 is to 37, which means that in the peak hour, 63% of the vehicles will go in one direction and 37% goes in the other direction, right? So the peak direction carries 63% of the total volume, right? So which means our D is 0.63, right? So it's a factor expressed as a ratio, right? So between a proportion in terms of 0 to 1, right? So 63% flows in the peak direction, right? So this is still a daily volume, right? So it is 63% of 31,000 vehicle flows in one direction per day in the peak direction, and we want to multiply it because we are calculating this for a hour, right? So for the peak hour, we need to use how much of this is flowing in the peak hour. So that is given as 12%, right? So 12% of this is flowing in the peak hour. So it is 31,000 times 0.63 into 0.12. So that gives you 2344 vehicles per hour, right? So this is a directional design hourly volume. So we design for this volume. So our capacities, should be able to accommodate 2344 vehicles per hour, right? So that's our design hourly. Okay. Any questions?
No, sir.
Okay. Okay, and this will be the last question for this session. So here we are trying to calculate the PHF and the related quantities. Okay, so we are given the traffic counts that were taken in different 15-minute period, right? So from 4 o'clock to 6 o'clock. Okay, so we have first 15 minute had 420, next 15 minute 475, and so on. So till 6 o'clock. So using this data, so we need to find out which is the peak hour, what is the volume in the peak hour, what is the peak flow rate within the peak hour, and what is the peak hour factor. Okay, so we can take three minutes. I think that should be fine. So if you have any doubt, you can ask. Otherwise, you can continue. Okay, so do you need more time?
Yes, sir.
Okay. Okay, so 0.978, I guess that's the PHF value that you have, right? So you have to have the other three also, which is the peak hour, which is what is the volume of that, and the peak flow rate also. So basically, you would have used all that to find PHF, but you just have to state that. Yeah, peak hour volume 1973. Okay, yeah, VHV 503. Okay, the time period, peak hour. Yeah, 4:30 to 5:30. Yes. So it's correct, except for the peak hour flow rate. So it's not 503, but it is 4 times of 503, right? So 503 is the peak flow in the peak period, right? So 4:30 to 5:30. Yeah, 4:30 to 5:30 is that hour where the highest hourly flow is taking place. So that is our peak hour, right? So 480 plus 490, 500 plus 503, that is the maximum flow that we have, considering all the different continuous 1 hour periods, like 4 to 5, 4:15 to 5:15, 4:30 to 5:30, and so on. So if you consider all the continuous 1 minute, 1 hour periods, then 4:30 to 5:30 has the highest hourly flow. So that is our peak hour, and so yeah, that is our peak hour. So the peak hour volume is basically the sum of the individual 15-minute period volumes, right? So that is 1973, the sum of these four values, 1, 2, 3, 4. The peak flow rate. So what is flow rate? So as we saw earlier, a flow rate is nothing but you measure the flow for a smaller period but express it in terms of hourly flow, right? So in this peak hour, so 503 vehicles is the maximum flow, right? That is our peak peak flow happening in the peak period, right? So 503. But when you want to express it as a peak flow rate, so you want to express it in vehicles per hour. But this 503 is not for 1 hour, right? So it is for a 15-minute period. So when we want to, project it for 1 hour, we have to multiply it by 4. Then we will get the hourly volume. So 503 times 4. So that is your, the peak flow rate, right? So that is 2012. Okay, so that's the only mistake. Other things are correct. And the peak hour factor. So what is peak hour factor? So it is the hourly flow by the peak flow rate, right? What is our hourly flow? So that is 1973. So that is the maximum flow, maximum hourly flow, and then divided by, this is your peak flow rate 2012. So that gives you 0.98. Okay, so yeah, so that was correct. Okay, any doubts, any questions? So we have come to the end of this session.
Last slide, sir. What is what answer? That slide alone can
Yeah,
be shown.
this one.
Sir.
Yeah, so peak hour is 4:30 to 5:30. Peak hour volume 1973. Peak flow rate 2012. And peak hour factor is 0.98. Yeah, okay. So with that, we have come to the end of week 2 session. So if you have any questions or doubts, you can ask. Yeah, and if there are nothing else, so we'll meet again next week. Okay, same time. And so in the meantime, if you have any doubts or questions that you want to ask, you can make use of the discussion forum. I'm sure that you are aware of it, right? So we have a discussion forum. So if you can post your questions in that, and during the week that will get answered. Okay. So if you go to the Swayam page of this course, you'll be able to find the link to the discussion forum. Yeah. So any questions or doubts that you have?
No, sir.
Okay. Yeah, so there is nothing else, so we can close this session. I thank you for attending, and we'll meet again next week. Okay, feel free to log.
Thank you, sir.
Thank you.